Imagine you're reading a book. To understand the current sentence, you need to remember the sentences that came before it, right? Our brains naturally process information sequentially, building context with each new piece of data. Traditional neural networks, however, struggle with this. They treat each input independently, like reading a book word by word without remembering anything that came previously. This is where recurrent neural networks, or RNNs, come in. RNNs are a special class of neural networks designed specifically to handle sequential data. Think of data where order matters, like sentences in a paragraph, stock prices over time, or even sequences of musical notes. Unlike feed-forward networks, RNNs have a kind of memory that allows them to retain information from previous steps in the sequence, and use it to influence the processing of current and future steps. The core idea behind an RNN is a simple loop. At each time step, the network receives an input, and also takes the output from the previous time step as an additional input. This creates a feedback loop, allowing information to persist. This internal state, often called the hidden state, acts as the network's memory. Let's visualize a simple RNN cell. It takes an input at the current time step, say, a word in a sentence, and combines it with the hidden state from the previous time step. This combined information is then processed to produce an output for the current time step and, crucially, to update the hidden state, which will be passed on to the next time step. This recurrent connection is what gives RNNs their power and understanding sequences. For example, when processing the sentence "the cat sat on the network, by remembering cat, can predict that the next word is likely mat or chair, rather than something unrelated like airplane. However, training these simple RNNs isn't always straightforward. A significant challenge is the vanishing and exploding gradient problem. During the backpropagation process, gradients, which are essential for updating the network's weights, can either become extremely small or extremely large as they are propagated through many time steps. A vanishing gradient means the network struggles to learn long-term dependencies. If a piece of information from early in a long sequence is crucial for a decision made much later, a vanishing gradient can prevent the network from effectively learning that connection. It's like trying to remember the first chapter of a book when you're at the last chapter, but your memory of the first chapter has faded completely. Conversely, an exploding gradient can cause the network's weights to become so large that training becomes unstable, leading to erratic predictions. Imagine trying to adjust a dial, but every tiny turn causes it to spin wildly out of control. While simple RNN cells have limitations, they form the foundational building blocks for more advanced architectures. Understanding their basic mechanism of processing sequential data with a form of memory is key to appreciating their capabilities. The applications of RNNs are vast. In natural language processing, they're used for machine translation, text generation, and sentiment analysis. For time series data, they excel at forecasting stock prices, predicting weather patterns, and analyzing audio signals. The intuition behind memory in neural networks, as embodied by RNNs, is profound. It allows machines to move beyond static, independent data points and engage with the dynamic, interconnected nature of real-world information. This fundamental concept of processing sequences and maintaining a state across time is the cornerstone of how RNNs learn from and interact with the continuous flow of data that surrounds us.